all, I would like to say a little bit that I come from the other direction than Wouter, because I come from the practical side. I'm a gardener. I'm a technician for landscape and gardening, and I came by working from the development of products and systems. I came to the research side, and now I'm quite a lot involved in research as well, but my concern is to connect the practical side and the research. So a little short introduction of what I will talk about today is introduce myself a little bit, what GREENPASS does, but I don't want to talk too much about GREENPASS. That may be another topic. Climate change, we have seen a little bit from Wouter already, so I don't have to talk too much about this. Then I come to the core of this presentation, is the positive effects of green and blue infrastructures in general, and then how green facades can improve the indoor temperatures, and how green roofs can as well improve the indoor temperatures. As I said, I'm a landscape technician. I have more than 35 years experience in green roofs. This was really my focus all over the years. And when I did research on new products, I met with people from the University of Vienna, and we said we have to bring these results into the practical reality. How can we use this information that how plants can help us, and to use it in the design in the very practical manner, the specific performance that each different type of greening, each different type of green or blue infrastructure can bring into our urban environment. And we developed something to make it visible, transparently visible, particularly for planners, for architects and designers, to see that how they can use the blue and green infrastructures and to choose the best solution. What GREENPASS does, we developed a tool and different methods to create climate resilient urban planning. We use it for developers, so the investors of buildings, they want to know it. More and more of them are really say it's so important. We have a reputation that our buildings have a negative impact on the urban environment. So we want to change it. It's necessary. Of course, architects as well, urban designers, they need to know it as well. It's a new field for them as well. And of course, municipalities. For example, Krefeld, quite close to the Dutch-German border, they started that they more or less wanted developers of big projects or buildings to prove that their buildings will not have a negative impact on the urban environment, so that the microclimate will not be getting worse. In the best case, these buildings will improve the microclimate. So we look at climate, which contains things like thermal load score, thermal comfort score. We have scores for that as well. Thermal performance, radiation, and so on. We look into water because flood prevention, particularly in the Netherlands, I know from Dutch colleagues, flood prevention is a really hot topic in the Netherlands as well for many years already. Of course, we look into the air. Wind is very important, particularly when we come to the situations how we feel the temperatures, because the temperatures we feel differ a lot from the temperatures that we can measure. Wind and shading and humidity is very important. That comes to what we call the physiological equivalent temperature, so how people feel the temperature. Of course, we look into biodiversities because we are green people. We come from the green side. For us, it's always important not to have a green that's decorative, but also has a really good impact on the biodiversity. We look into energy. Energy is also a topic today because heat is energy, energy is heat, and how we can reduce the outdoor energy and the heat so that it can be converted or transformed into the interior of the buildings. And of course, we also look into costs. So we not simply say you have to green everything and then it's perfect. Of course, you have in the real world, you have to look into the costs. So we trying to find out what is the optimal, what is the perfect solution between the costs and the performance. This is what we, for example, do. You see on the left-hand side above, you see a simulation where you still see a lot of orange areas in the streets, which are a little bit hot, too warm. And on the right, you see that can you see my mouse, by the way? Okay. Yeah. You see, there are less warm areas. It's, of course, the shape of the buildings, the design of the buildings has changed a little bit to allow more airflow, but the main reason why it's cooler here in the street is that we changed the trees from acer trees to gledicia trees, which have a more which are more open and which have a higher evaporation rate. So simply by changing the type of trees, you can make it cooler. And this is, for example, on here we see the simulation model. We simulate the temperatures during the day. We simulate the temperatures at 10 o'clock in the evening when you go to bed. We analyze the wind, and then, of course, we get, by, how to say, combining different analyses, we can measure or find out about the so-called felt the temperatures, how we feel the temperatures, the physiological equivalent temperatures. And then we see how many areas are warm or slightly warm, which are cool, which are good and not so good. And the result is, for example, is here in Vienna, just finished the IKEA. It's a new IKEA store inside the city, a quite small one. It doesn't have any parking. So IKEA said it's close to the railway station. People can come here by public transport. We don't provide parking and we deliver the goods. This saves a lot of carbon dioxide. And the problem was, before IKEA built this, the people who live around this and the other shop owners, they said, we want to have a park. We don't want to have a new building here. It's already very dense. So the idea of the architect was, he said, I built an IKEA and I will bring a park as well. So in the end, we have more trees on this space than a park on the ground could have. And you can see here the stairs, it's 24/7, it's open for the public. And we measured this, that we can reduce the temperatures up to 1.5 degrees Celsius, which means that the temperature you feel is around 12 degrees cooler. So you can combine buildings and a good environment. This is a lot of discussion nowadays because we say we don't want to seal additional surface on the landscape. We have to have a higher density in the city to make use of it. But then people complain and say the living quality, it's not so livable anymore. But if you do it in a smart way, everybody can be happy. Or for example, a new living area, it's called the Biotop City. I heard there is one going to be built in Amsterdam as well, a Biotop City. In Vienna, they already start with the construction. And here we even reduce the temperature more than 2 degrees. But today we will talk about a little bit about the indoor environment and the temperatures. We know in the last 3 summers and some summers before that it's getting hotter, but the problem for us is not just this 1 or 2, or it will probably 3 degrees or more hotter in the future. The problem is really that we have these long heat periods. The city really heats up, absorbs all the energy over the time, and this heat is reflected into our urban environment over the time, and it loads up. So the gap between the natural temperature and the temperature in our city is getting wider and wider. But we know that plants are a kind of natural air conditioning, which I will explain a little bit more later. And if we use more green in our cities, we can reduce the temperature significantly. There's not much to explain about this because Wouter explained a little bit to us how the temperatures have an influence on our health, on our performance, how we can focus, how we can concentrate on our work. It is very, very important. But this energy comes from the sun, but then it's converted into noticeable heat, the temperatures that we feel, the latent heat. That means the temperature, the heat that is reflected from the ground and from the buildings onto our body. We always had higher temperatures in the city. Everybody knows it when you ride your bicycle late in the evening from the city to the landscape. If you live on the countryside and you met with friends in the city, for example, when you ride your bicycle in the evening out, you feel it's much cooler than in the city. In the daytime, you feel it as well, or everybody knows how much cooler it is in the forest in the summer. But it was more or less parallel, always a few degrees warmer in the city than on the countryside, because we had a few weeks of sun, then the rain comes, it cools down, we had a little bit of sun again and rain and so on. But today, the problem is that we have these much longer heat periods. So the gap between the temperatures in the cities and the natural temperatures is also widening more and more. Wouter has shown this, that we will have more heat waves, that we have more what we call tropical nights. Tropical nights are those nights which stay above 20 degrees. And if we cannot recover during the night, that really also has a very strong impact, negative impact on our health. For example, we have some figures about Berlin from the year 2018. In Berlin, we had 490 heat fatalities. On the other side, we only, of course, that's also bad, but we had 45 fatalities from traffic. And this will increase everywhere in Middle Europe, that we have more and more heat and that we have more and more heat fatalities in the future. So what we have today is, we have a poor climate resilience in our cities. We have the impacts, the negative impacts of heat waves, floodings as well. This has a lot of health effects. We need a strategy to control the climate and adaptation measures to keep our cities livable. As I said, plants are very effective. And why are the plants so effective? It's that water can vaporize without boiling. You don't have to heat the water up to 100 degrees to make it boiling. Everybody can feel it more or less every day on your skin. When you're sweating, the water vaporizes, although it's not boiling. And then it absorbs a lot of energy from the ambient air. It reduces the temperature because it takes literally the air out of the energy out of the air, and then it vaporizes, and it's going much higher into the atmosphere where it builds clouds, which has also positive effects. So if you compare the temperature under an umbrella or another shading which has the same shade as a tree, under the tree it's always a few centigrades cooler because of the vaporization of the trees, of the leaves. It's all known, or many people know it by now. So we have a lot of strategies. We have grants that we get public money to make our cities greener, but it's not mandatory. It's more or less, you can decide if you do it or if you don't do it. Then a lot of developers say, so why should I do it? Why shouldn't the others do it as well? And so on. But of course, fortunately, it's changing. But what we need are figures and data that we can really say how it works on your project when you design the project. And the question is, where exactly do we need the green? Which kind of? So different types of greening have different characteristics and capacities, and how much, because money is not endless. There's another example here. For example, when we plan with a normal green, we see how warm it was under the trees here. We have some cool spots. The shading of the building itself is also very important. When you have a little bit more green, it's getting better, but you still have some hotspots in between. But when you optimize this, you can reduce the temperature. So we say it's a natural air conditioning for the city. Not only the people who live in this area have an advantage, also the people who live around. Of course, there are some simple planning basics. Wind is very important to have a good wind flow. Very often we make a wind analysis before the designer starts to create just a sketch of the layout of the buildings. The wind direction is very, very important. Open building structures and align the openings. The height of the building is important, but more important is the width of the building openings, that we have a good ventilation. Open space is important. Trees, shrubs, plantings, green facades can help a lot. Green roofs can help. The surface materials is also very important. Also the albedos, if the reflection of, particularly of the roofs, can be important, or the horizontal installed materials is very important. Blue infrastructures, technical shading as well. And usually you can do a lot when you plant some trees on the north, on the south and on the southwest side of the building. So when you want to have trees, you can consider which is the best location for my trees. If you can't plant trees because it's very dense, or you have some pipes and in the ground where you cannot plant trees, think about having a green facade or having a green roof. I come to the facades now. We know that the facades do a lot good for our environment, reduce the temperatures. It's good for flora and fauna, for the biodiversity. Carbon sequestration is definitely there, and the insulating effect in the winter, I will show later what green facades can do on this, and of course insulating effects in the summer. When you look at the temperatures of different surfaces, this is more or less for a roof, but when you see a roof that is covered with gravel, the temperature is much, much higher than a green surface. Bitumen, this is about the reflection. Bitumen roofs, they don't reflect, these black roofs don't reflect the radiation, so they absorb the energy. Of course, green surfaces don't have a good reflection, but they convert the energy into cooling, because they vaporize water. The cooling effect is therefore very, very important. So the vaporization is important by the plants, that we activate the plants, that we have to bring also sometimes water to the plants, but we have to use natural ways. For example, it's important that we don't drain the water into our sewers quickly. We have to make use of the rainwater as well. We have to collect the rainwater. We have to infiltrate rainwater into the ground so that the plants can later use it. Green walls also have other benefits. For example, noise reduction. They absorb the sound waves and don't reflect the noise that much. So the noise reflection, or the sound reduction, is also a positive side effect. Here we have done a study of a city, of a street in Vienna. It's a very populated, it's a shopping street, where we simulated, if we would have more green facades, how the temperatures will be reduced. And the so-called PET, the physiological equivalent temperature, so the temperature that you feel, will be 13 degrees cooler if you have more green facade in the cities, because trees are not possible. Sometimes it's too dense and there's not enough space for trees. There are water and electricity in the ground. So green facades can be a very good solution to reduce the temperatures. And here you see a bare facade. The radiation from the sun is, depending on the albedo, how bright or light it is, transferred into heat. It heats up the ambient air. Some of the light is reflected depending how bright the surface is, but then also converted into heat. A little bit of heat is stored in the ground and reflected then in the night. But of course, a lot of heat also goes into the building, and it's getting warm inside the building. If you have a green facade, only a little bit of the heat goes into the building because it's first of all, it cools the air. Not so much light is reflected on the ground. A lot of energy is transferred into vaporization. And of course, you have a kind of air cushion between additional thermal insulation between the green and the actual facade. It's also important. Some people say, okay, I have a white facade, so the building doesn't heat up. That's true, but a lot of light is reflected onto the ground and then reflected as heat into the environment. So that's not the best solution. With a green facade, most of the energy is converted into vaporization, into cooling. Trees can do the same, more or less, but again, the question is, do we have enough space for the trees? The trees are usually the cheapest way because they have a wider leaf area, much more leaves, more space to vaporize water, but as I said, it's not always possible. We compared also in Vienna in the year 2012 already different facade greening system with a white facade, and you see the albedo, of course, this is the solar radiation, and the white wall reflects the most, and the different green systems absorb the light but convert this into cooling because they are green. And this is how you see the temperatures, a white facade and with the green. So the wall temperature is much, much lower if you have a green facade. There's a similar or more practical research done by Professor Edelmann and Minka Adusopoko in Bonn. They also measured the temperatures on the green facade and under the ivy, under the plants. And you here see also the difference on the non-green facade and on the green facade, how the temperatures under the green are much, much cooler. This is also on 3 warmer days, you can see that the temperature on the non-green facade is getting much, much higher than on the green facade. And this is on the cooler days, you also see that you save a lot of energy if you have a green facade for cooling in the summer.
Peter, 2 more minutes, please. Yeah.
Okay. This is then for heating. You see the effect in the winter as well, that you save a lot of energy. So it's not good for cooling. These are all these benefits that you have from green facades. And if you compare them with a naked facade. In Vienna, we've done the same, even more deeper. It goes into the so-called U value, the insulation factor. And you see that in the winter, you have an improvement of up to 28% improvement of the U value. And in the summer, it goes up to 33% increase or improvement of the U value. Of course, the plants need some water. They vaporize up to 50 liters of water on a warm summer day. But you see here on the thermograph how warm the surface is on the ungreened area. Very interesting is also a project in Berlin-Adlershof where they compared conventional shading with a green shading. And you also see here that the heating energy behind the green facade is much lesser than compared to the traditional or conventional shading systems. Also, again, here the temperature comparison on the glass behind the green facade. The glass is warming up and transferring the heat into the building. The problem today is that we cannot simply compare this with our standards. The standards that we have are made for hard surfaces, for windows, for stones, and so on. So the problem is today that it's not in the standards that it will be accepted by the authorities as an additional thermal insulation. Okay. And you see here the cost, operating cost for the green facade was only 1,300 euros per year, while keeping up the conventional shading cost you 16,000 per year. So it's a win-win-win for everybody. Now I quickly come to the green roofs. It's a more or less the same effect, but I want to show a project in Mönchengladbach, not far, where the owner approached me and said, it's getting too hot in our buildings. It's all industrial halls. They have a very poor thermal insulation because it's a very old building. And he heard about that we can do something good with the green roofs. I said, okay, we can simulate this, but he said that, no, I don't want to simulate this, I want to try it. And these old industrial halls are 18,000 square meters, and we tried 450 square meters because there's a closed room underneath this, and so we can compare how it works and what is the real performance. I installed some so-called data loggers on the green roofs, in the air, under the green roof, inside the buildings, and we did the same on the other side where we don't have a green roof. So these are where we installed the data loggers, and these are the results that you see. The air temperatures 1 meter above is also cooler on the above the green roof than on the black roof. That means that we cool the outside as well, of course, but what's more important is how will it perform inside. This is the temperatures on the waterproofing, so less stress for the waterproofing. That means that the waterproofing will also last much longer, 3 times up to 5 times longer, so that you don't have to repair the roof that often, or actually never if you have a green roof. And here are the temperatures we measured in September. Unfortunately, we have installed this, we finished this at the end of August last year, so after the summer, but in September we had a few warmer days and we measured the temperature inside the building. And you see also inside the building that the temperatures are really much lower. You can see from inside the warm roof, which is not green, and here you see how the roof behaves with the greening. Yeah. And also you save a lot of energy in the winter. This is in just February, we've taken this measurement from our data loggers, and you can see that also the temperature difference on the waterproofing is a lot, so that the green roof insulates a lot, and even inside the building you see that the temperature under the green roof doesn't drop that much, so you save a lot of energy that way as well in the winter. Yeah. So you can see as a conclusion, inside we expect in the summer it will be 7 degrees cooler just because of the roof, the green roof. It saves a lot of heating in the winter. It prolongs the life expectancy of the waterproofing 3 to 5 times. The cooling of the outside is there as well. It reduces the water runoff and has a lot more benefits as well. Okay, that's it. Thank you very much.
Thank you, Peter. I'm also sure that you could talk about this all day, and it's a really interesting topic. I see it also in the questions that are coming in. I go to the quickly to the questions. One question from Richard Laroy. He asked about the IKEA project. Any idea about additional costs in a project like IKEA? It's of course a classical one. The budget approach. What does it cost? But I think you showed us that it also has benefits on the operational costs, like lower energy cost and savings like that. But if you compare it to a normal building, can you say something about that, or is it difficult?
Sure. I mean, IKEA is really very special. I think IKEA has also considered if they want, if you compare this building and you say, I will make a traditional, just a gray box inside the city, it would be much cheaper, of course. On the other hand, IKEA may not get the permission to build this building anyway, or they have a lot of objections against the building. So this was also probably a kind of economical decision from IKEA to do this. But we know that when you compare the costs for the green and the cost for the buildings, it's really very, very little. When you calculate a living area where you spend 3,000, 4,000 euros per square meter for the buildings itself, and when you then transfer the cost of the greening, it's around just like 2, maximum 3% if you have a good greening for the overall cost of the building. And if you make it very good, it doesn't have to be more expensive. This is why we calculate and we simulate what greening is the best in these situations. We had projects where the architects or the investor of the buildings, they approached us and we have a really very nice design for the greening here, but sorry, it's 30% over our budget. But we want to keep this microclimate performance. And by optimizing this, we could reduce the cost almost 30% and keeping 96% of this microclimate performance just by optimizing this.
Yeah.
So this is more expensive.
Yeah, that's always a combination. I go to the last question. I saw Christoph Dix. There's a lot of questions. An interesting one. What has a higher effect, trees in front of a building or a green facade? You were telling sometimes it's not possible to plant trees because of the infrastructure below the surface. So is it comparable, green walls or trees?
To a certain extent, it is comparable. I mean, a tree usually has much more leaf area, so more space or surface to cool the air, to vaporize water. And a tree is usually, when you just compare the leaf area, a tree is cheaper than a green facade. But the problem is, can you plant the tree there? And a tree which is standing in front of the building, if it's too far away, does not have such a good impact benefits for the building itself. So you always have to calculate what is the best solution. A tree, for example, you can sit under the tree and enjoy the lunchtime under the shade of the tree. That's another benefit which a green facade cannot deliver. But in general, yes, a tree is cheaper if you compare just the performance of the cooling effect, but you have to look into the details of each project.
Okay, and you can calculate that based on the plan of the street. Okay, then another questions. The last one for me. What has a higher let me see. Yeah, also from Christoph Dix. Trees are producing also humidity and they are cooling down the air, but increasing humidity is perceived as similar to increasing temperature. What is the balance of both effects, reduced temperature versus increased humidity? So otherwise it's getting more humid. Doesn't it feel more uncomfortable?
That's true. There is a certain degree of humidity that when you feel uncomfortable, but it depends a lot also on the wind. If you have more wind, high humidity doesn't feel bad, it feels good, in fact. If you don't have wind, even 85% of humidity, you may feel uncomfortable. So wind is always very, very crucial when you build or when you design the buildings. And we always make a very detailed wind calculations, and we find out where are the people, for example, where are the playgrounds. So we have to have more wind there than in these areas where the people usually don't stay. But you have to sometimes accept strong winds between the buildings, but not having areas where people are, how to say, stay a lot of time. So that's also a question when you design the wind, is where are the people, how to say, spend a lot of time, where are just passing through areas and so on. So you can also plant trees in the wrong place if you stop the wind between the buildings, for example. So humidity and wind depends a little bit on each other.
Okay, thank you, Peter. So it is always a combination, green, wind, etc.